Hello, everyone, and thank you for joining. We will take a couple of minutes to let folks arrive and come in, grab their sandwiches, use the facilities, and then we will get started. I figure while we are letting people arrive, I'm going to talk a little bit about Prepare's conference that is coming up this October. So for those of you who are familiar with Prepare already, we are a 501c3 based in St. Louis, Missouri. We have been around for about 3 years, and we focus on, our mission is to increase collaboration around AI and other fourth industrial revolution technologies in order to advance the human experience. We do this with the help of a number of sponsors and incredible organizations, including Daugherty Business Solutions. And Daugherty this year is one of our platinum sponsors. So I'm going to talk a bit about the conference while people are getting logged in and hooked up. And then we will get directly into this awesome session. So let's see, we are kicking off. If you all go to Prepare.Ai, you'll see all the information about our digital conference this year. We're actually doing things a little differently. We are spreading the content out over 5 afternoons, over 5 weeks in October. So we're making things a little more bite-sized. The other really exciting thing is that all of the content will be viewable on your own time frame. So even if there are sessions that you have conflicts for, you might have class, you might have meetings, you can always view the content later. So this year, like I said, we're doing 5 sessions. We're kicking things off on Thursday, October 1st with a fantastic free event sponsored by Daugherty. It's our workforce development forum on how to grow the tech talent pipeline. Wednesday, October 7th, we'll spend the afternoon discussing geospatial discoveries in the Our Planet and Beyond track. I'm so excited about this track. We'll talk about how AI is impacting food security in the context of a warming climate, and how AI is helping scientists discover ancient civilizations from satellites with space archaeologist Sarah Parkak. She's just amazing. Wednesday, October 14th is our health and well-being track. That'll feature conversations on open science, the science of behavior change, computer vision and diagnostics, and of course, how AI is being utilized to combat the spread of COVID-19. On Wednesday, October 21st, is our AI at Work and Home session, featuring a Chief Data Officer panel, also hosted by Daugherty, with the chief data scientists of MasterCard, Cigna, RGAX. We've also got sessions from incredible practitioners at Facebook, Square, Netflix, just to name a few. We're closing out that day with a keynote from Marlon West, the head of effects animation at Disney. His teams built the oceans. His team worked with the coders who spent a year building the algorithms that built the oceans in Moana. They spent a year, building the algorithms. The algorithms got the ocean 80% of the way there, and then Marlon's artists could really spend their energy on that final 20%, what only humans can do. It's such a great story. And then our final session is on Wednesday, October 28th, 6 days before the 2020 election, where we'll focus on social impact and ethical implications of AI. So conversations will include, the impact of bias in algorithms, deepfakes in political movements and elections. It should be really fascinating. So I want you all to come. We are running a secret flash sale just today for those of you on this webinar. If you put in coupon code IMAGE, you will get $100 off the $179 ticket. So $79 for about 80 hours of content should be pretty phenomenal. Okay, now I'm going to get into today's webinar. I'll just do some quick introductions. This is our last webinar of the summer. A picture is worth 1,000 words, image analysis with OpenCV, presented by our friends at Daugherty. So a little bit of administrative stuff. Hold your questions for the end. You can ask them throughout, but we will actually be answering them in a Q&A session at the end. If you're having trouble seeing all of our panelists, click the gallery view at the top right. If you have any questions or need any help, just use the Q&A as well. So today we have with us Sandeep Singh. Sandeep is a principal consultant at Daugherty Business Solutions, where he brings deep experience in biotech, hospitality, finance, and aerospace. He's been a part of multiple space missions with NASA and has developed statistical techniques to discover organics on Titan using hyperspectral and imagery data. He holds a bachelor's in physics, mathematics, and astronomy from Northern Arizona University, a PhD in space and planetary sciences from the University of Arkansas, and an MBA from the Olin School of Business right here in St. Louis, Missouri. And then we have with us Benjamin Weinert. He is a consultant and data scientist with Daugherty Business Solutions, where he implements machine learning, statistical, and modeling techniques. Past projects of his include using multiple techniques to generate synthetic data, using image recognition and recommendation engines, as well as building forecasting models. Benjamin holds a bachelor's degrees in physics and math from the University of Rochester, and master's and PhDs in physics from Indiana University, Bloomington. And then finally with us today, we have Angelique Zeringue, who is also a data scientist at Daugherty Solutions and is an accomplished data analysis data analyst, using techniques including inferential statistical modeling, clustering, predictive modeling, and other machine learning and data analytic techniques. Angelique holds a bachelor's degree from Northern Arizona University, a master's of science in biostatistics from the University of Minnesota, and a PhD in public health and biostatistics from St. Louis University. And now I will hand things off to Sandeep.
Thanks, Cindy. Wonderful introductions, and welcome everyone for the part 2 of the webinar series that we did on geospatial analysis. So last week we talked about geospatial analysis, and this week we're going to talk about image analysis. And Ben is our expert in when it comes to extracting information from any type of images. So let me introduce Daugherty a little bit here. Daugherty is a technology-focused consulting company right here headquartered in St. Louis. So we've been in business for over 35 years, and we deliver both business strategy and hands-on implementation. We have several locations around US, Atlanta, Chicago, Minneapolis, Dallas, New York, New Jersey. We have about 1,300 and counting consultants here, and we deliver local hybrid delivery model through Dev Center, Innovation Hub, and at client sites. So introducing the scope of this talk, Ben, you can actually share your screen if whenever, if you can. So the brief introduction about this talk is going to be around giving you the ability to understand how to extract information from images. So Ben and Angelique are going to introduce you to what is the image analysis with OpenCV, of course, and the methods for extracting information from images. Angelique is going to talk about how raster geospatial images have some sort of information and tie it back to our part 1 and part 2 of the series, and then applications of OpenCV and other machine learning techniques to raster data. So I wanted to say a word about the scope of this talks is basically an introductory and giving you the tools to explore images on your own. So general understanding of what computer vision is and techniques for analyzing images using OpenCV, and basic understanding of raster data, how raster data has some information that you can extract using some of the tools that Ben is going to talk about. And then of course the use cases for OpenCV with some geospatial data. And I will hand it over to Ben now.
Sure thing. So first things first, why are we here? What is image analysis? It's the practice of extracting useful information from images. Now, useful is an interesting term because it can mean a lot of different things depending on what your analysis is. It can mean segmenting your image and extracting the object you're looking for from that image. It could mean creating human readable features to describe your image. Or it could mean just creating features that are just for machine learning, where it's not necessarily something that's human understandable. I like to split image analysis into two sections: processing images to enhance them for analysis, and creating features from the images. So some examples of what image analysis can do: optical character recognition, computer vision. Common things you'll see on Kaggle are tumor detection, motion detection, segmentation of aerial photos, self-driving cars, etc. You could do a lot with image analysis. So now that we know about image analysis, why OpenCV? Well, images are just arrays, and we can treat them that way. This means that we can perform mathematical operations on them if we wanted to. It's pretty straightforward to do something like calculating the mean and standard deviation of color, subtracting background noise, rotating or resizing. But if you want to do something more complicated, let's say you want to build a kernel with a shape template in it, it is possible that you'd use a sliding window to find out where that object is in the image, but things get more complicated and it takes a lot more time to implement. So libraries like OpenCV allow for more complicated analyses. OpenCV is really good because there's a lot of documentation on it, and it's available in Python, C++, and Java. So it has a lot of support. It allows for transformation, segmentation. It even has a bunch of built-in algorithms and has its own neural network package that you can import neural networks into. So starting your analysis, one of the first things you do is you read in your image and you choose your color space. One thing to note that is a little bit odd about OpenCV is that the default is that it reads blue, green, red, BGR, instead of RGB. If you're going to use something like matplotlib to show an image that you read into OpenCV, you'll have to flip it, convert it from BGR to RGB. Otherwise, the image will look a bit weird. So the reason why we care about color spaces is because they can provide different benefits. A common thing to do is to grayscale an image. So instead of having 3 color dimensions, you can just create 1 intensity dimension. This is helpful because it reduces the dimensionality of your image. So if you're just doing something that color is not important for, so let's say you're trying to find boundaries or just looking at the shape of objects, color is probably not going to be helpful there. If you're doing something like trying to identify an orange cat versus a black cat, you're probably going to want color in there. Removing color, though, removes a little bit of the dimensionality, which allows the algorithm to learn quicker. So MNIST is a good example of this. MNIST is a data set of handwritten digits. So if they were color digits, does that color really add anything to trying to determine if a 4 is a 4? Not really. This would be an appropriate example to grayscale an image. It's pretty easy to do in OpenCV. They have a convert color function, and you just tell it what you're converting from and what you want to convert to. One common thing you want to do with grayscale images is remove background. So you can do this via thresholding, where you set a threshold to extract only objects within a specific intensity range. Now you have to determine what you want to do with that threshold. Usually when you set that threshold, anything above it goes to a specific value, usually 255 for completely black. Anything below gets set to 0 for white. That's known as binary. There are other options you can choose, like truncated, where it's more of a gradient scale. So in the images here, we have a picture of a Sudoku board, and you can see it's a little bit in shadow. We can apply a global threshold where we set the value to 127, so halfway between 0 and 255. And we say anything above 127 we want to keep. You can see on the right-hand side of the image, it does decently well. at removing some of that background and only keeping the areas we care about. But on the left side, it fails a little bit and everything is black. The reason for that is because the left-hand side is in a darker shadow, so more of it is above that threshold than on the right side. For this reason, you don't always have to use a global threshold. You can use adaptive thresholds. Adaptive thresholds determine the threshold by the region around the pixel, instead of just setting a specific value, saying everything above 127 make black. When doing that, you can choose how you want to use your adaptive threshold. You can choose mean value or a Gaussian weighted. And you can see the bottom two diagrams are the mean thresholding and the Gaussian, and they do a much better job than a global threshold. One thing to note is that it is possible to have two separate thresholds, and that's known as Otsu's binarization, and you can just pass that option to your threshold method if you need to. So if you don't want to just remove background, but you want to actually extract an object from an image, that's known as segmenting. One common thing to do when you're trying to segment is to transform to the hue saturation value color space instead of BGR. The reason for this is it's easier to separate color from lighting conditions. So you could have the same, let's say, magenta shirt, but depending on the lighting you're in, it could look like a different color. That gets a little more complicated to do in BGR, but the HSV color space puts all of the color into the hue, and saturation and value take care of lighting conditions. So you can separate that out more easily. A good example of this, if everybody remembers the dress that was big on the internet, was it white and gold, blue and black? A lot of that was due to lighting conditions. So to segment your image, you first convert to HSV using the convert color, and then you define a range for the colors you want to keep. So in this case, we're trying to extract out the blue circle right there, and you choose a lower blue range and an upper blue range. Then you can use OpenCV's in-range function to create a binary mask. And you can see here, it's binary mask for that blue circle. By applying a bitwise AND of your mask to your original image, you can extract just the object you care about. So some use cases for this are object tracking. If you're doing this, it makes it easier to follow that blue circle around the image if it's moving. You could do it for feature creation, or you could remove background for neural networks when you're trying to learn from an image. Another thing to think of is that images are rarely clean. So when you get them, usually you're going to want to do one of two things. You're going to want to either blur it or smooth it, or you want to sharpen it. Blurring is useful because it can help remove noise. You see in this example here on the left, the edges are a bit jagged. By blurring it, you kind of remove that jagged shape. So this is useful for if you want to fit for a shape of an object or find do a boundary detection. You usually end up blurring your image first just to smooth the edges. To do this, you can define a custom 2D filter, or you could use the blur method, which just takes an average within a kernel. You can apply Gaussian filtering instead of just a straight average using the Gaussian blur option. Or you can use the median value using median blur. One thing to note about using the average or the Gaussian is that can create values that weren't originally in your image. The median, though, will only replace with values that are already in your image. So that's usually more useful when you have what's known as salt and pepper noise. You can think of applying a constant static to your image. Median blurring will do better on a static and removing that. You can also sharpen your image to increase the contrast, depending on what your goal is. And you can do that by taking your original image and subtracting out a weighted blurred image from that. So that will increase the contrast in your image. So now that we've cleaned our image, we can transform it to be something slightly more useful using a morphological transformation. The first thing you're going to want to do is you're going to want to define a kernel. You can choose the size of the kernel and the shape of the kernel using a structuring element. Common ones are ellipse, rectangle, cross, depending on how big you want this effect to be and what area you want it to cover. Once you've defined your kernel, you can find your transformation. So in the top left corner here is our original image of a script J. The erosion transformation takes the kernel and it sets, if there's any value that's 0 in your image, in the kernel, it sets all the values in that kernel to 0. So what that does is it thins out your image. So what that's useful for is increasing the separation between objects, or if you have any artifacts, let's say from lighting, it can help remove that. It's also useful for if you're trying to separate out objects, you know that the thinned out version, you're highly confident in that being its own entity if objects are touching. Dilation is the opposite. It takes your kernel and it says if anything in this kernel is 1, then non-zero, then everything in this kernel is non-zero. So what that does is it increases the area of your object. So if you want to make sure that you extract all of your object from the image, dilation is helpful. Opening is a combination of erosion followed by dilation. That's useful for removing noise. So here, and you see that we have an image of the J with a bunch of white dots representing noise. Because this shrinks the image and then expands it back to the normal size, the noise disappears. Closing is the opposite. It's a dilation followed by an erosion. That's useful for filling holes in your image. So in the image in the middle right row, you can see that there's missing values in the J, and that gets removed after you apply a closing transformation. Gradients keep only the edges of your image, so it's useful for boundary detection. And then you have some combinations called top hat and black hat. Top hat is your original image minus the opening. So what that's useful for is highlighting small bright objects in your image. So in the opening image, if you want to only keep the dots and not keep the big J, you can apply a top hat. Black hat is the closing minus the image. So that highlights small dark objects. Example being, if you had a sign with some black text on it, this would help extract out just the black text. So now that we have our image processed, let's talk a little bit about gradients. Gradients are necessary for edge detection and contour detection in images, so they're important to understand. The reason why we're interested in gradients is because they represent areas of change. The bigger the area of change is, the more information it can give to us about what's happening in the image. You can think of gradients as almost passing a high-pass filter over your image. So 2 common filters that are used to extract the gradients are the Sobel and the Laplacian. The Sobel is a first-order derivative of your image. For this, it has a separate X filter and a Y filter. So top left in this image is your original Sudoku board, and the bottom is your Sobel X of the image and your Sobel Y of the image. So you can see the Sobel X looks for change over the X direction, so it extracts out all of your vertical lines. The Sobel Y looks for change in the Y direction, so it ends up extracting out your horizontal lines. So you might be wondering why we have X and Y filters. This is useful because if we square the values, we can get the magnitude. But because we have a separate X and a Y, we can also get the direction of the gradient. The Laplacian filter, which is the top right, is the second order derivative. Unlike the Sobel filter, this is only a single filter, so we don't have a separate X and Y. This results in much finer edges, but we lose out any information about the direction of the gradient. So that's something to consider when you're using a Laplacian filter. Also, because it's a second order derivative, it can be sensitive to noise. So now that we have gradients, we can talk about edges. So the difference between a gradient and edge is an edge is the maximum, the area of the gradient. You're looking for boundaries here. So we use gradients to determine if a point belongs to an edge. The general method for canny edge detection is first you smooth your image using a Gaussian blur to remove many of the jagged edges. Then you get the magnitude and direction of the gradient from the Sobel filter. You use non-maximum suppression to remove points not associated with the image. So in this top image here, half the image is green, and then you see it changes to white. So we're looking for the edge between the green and the white. So we know that the gradient is going to be along the horizontal direction, which is the direction of the change, and the edge will be in the vertical direction. Using maximum suppression, we look for what is the largest value, A, B, or C, along the direction of the gradient, and that will be A. So it removes the two other points. Then you also apply hysteresis thresholding. What this does is you set a min value and a max value. Any value that is above the max value is counted as an edge. Any below the min value is ignored. It's not part of an edge. The change in the gradient is not big enough. Points that are in between, if they are connected to a strong edge, are considered part of the edge. So in this case, C is connected to A, so that would be considered an edge point. B is not, so that is not an edge point. So examples of canny edge detection, you can think of self-driving cars. There's a lot of examples of people using this when they're trying to find lanes in an image in order to drive. So here we have an example of canny edge detection. You see the left is a grayscaled image, and all that's done is you apply the min value of 100 and the max value of 200 and extracts the edges. One thing to note is that since you set these values, you don't get all the edges of the crowd, since that's removed by the min cut. It focuses more on the areas of large gradient changes, which is the person in front. Contours are also useful. So contours are similar to edges, but they form a closed object. Again, like with edges, you first apply grayscaling, but then you also apply an edge detection and pass that to your contour finder. Contours are useful because they have properties which can be used for feature engineering, as well as helping to extract images. Additionally, they have a hierarchy. So if we go back to the canny edge detection picture here, you can see not only do we get the edge of the person, but we also get a lot of edges of the creases on his shirt. That's not necessarily going to be helpful to us. So if you want to, you can say, give me only the external contours. So any contour that is not within a bigger contour. And that will remove all of those inner edges. Here we have an example of how to code it. And you see, first it's a grayscaled image. You apply a canny detection. And then you pass the edges to the canny, the fine contours method. And you choose how you want to handle the hierarchy. In this case, the external means only give me the external contours, and how you want to store the contours. So I had mentioned that contours have properties. Here are some examples of them. Contours have image moments, which are weighted averages of the intensity. This is useful because you can get things like the center of a contour. So from that, you can measure the distances between multiple objects in your image. You can say that you only care about objects that are within a certain region of your image and remove anything else. You can get the area of a contour, the perimeter. You can approximate the contour shape. So in case you don't want the exact contour, but you want a close shape to it, you can use that to approximate the shape here. You see an example in the top left from contour approximation, it says it's close to a rectangle. You can get the bounding shapes, so the minimum enclosing circle, square, oval, the min-max values. You can even apply template matching. So this is useful because you can see sort of that you can build up features to describe the objects in your image. From this, you can create a data set that you can then pass to any analysis you want to describe that image. A little bit about hue transformations. So it's rare that you get an exact shape that you're looking for. Example is if you're looking for lanes when you're driving and you have dashed lines, or a circle that's not exactly a circle, maybe a part of it's missing, or maybe it's slightly off shape. So hue transformation is a method to detect imperfect instances of any shape via voting algorithm. Now, common shapes to look for are lines, circles, and ellipses, and these are available in OpenCV. So I'll talk about hue line transformation. So any line could be represented in the Cartesian coordinates, y equals mx plus b, or the polar coordinates, r equals x cosine theta plus y sine theta. For this, we're going to use polar coordinates. The reason being that polar coordinates don't have an issue with the slope approaching infinity when you have a vertical line. To do this, we first create a 2D array of all possible r and theta values, where you have to specify what granularity you want of r and theta. Then we loop through each point in the image. So here we have 3 points. You can see them kind of on the blue line. So for each point, we loop through each bin of theta and calculate the r value between the origin and the normal line. We increment the bin for all r theta pairs. Then you loop to the next data point and you do the same analysis. And then on the right side, the final point. Finally, you set a threshold for how often does a r theta pair have to belong for me to count it as a line. So in this case, you can see for theta equals 60, it's all about the same level of r at around 400. So that would pass the threshold cut here. While for theta equals 15, the first data point has an r of 189, and the second value has an r of 318. So theta 15 wouldn't be allowed. For circles, you just change the formula you're looking for. In this case, it'd be x minus x center squared plus y minus y center squared equals r squared. So hue transformations are shown here. You see on the left, we have a hue line transformation. And you can notice that it isn't perfect. It actually, the words on the right side of the image are close enough that it reads that as a straight line. On the right, we have a hue circle transformation, and you can see it extracts out most of the circular values. The C's in the OpenCV logo, which aren't quite closed, are read in as circles. So putting this all together, you can now start creating your own features based upon contour properties. General things to keep in mind are color, texture, and shape. Color being average RGB, standard deviation of it. Color gradients, you can use HSV instead. Shape being how many objects did you find? Maybe objects that matched a certain template. What was the area and perimeter of your contours? The solidity, which is the contour area of the whole. Aspect ratios, general shape parameters, etc. You could also look at texture. So OpenCV, I think, has this in as a package. I personally use skimage for texture. What you do is you build up a gray co-occurrence matrix, which is how often do values of gray level intensities appear in adjacent pixels. And from that, you can get a measure of dissimilarity. So how much of a difference is there between adjacent pixels, the correlation, the entropy or randomness of pixels in your image, and the homogeneity. So from this, you can start building up features that you can run an analysis on. You can build up a data set and you can pass it to an SVM, a neural network, whatever you want to do. And you can build features from this that are a little more human interpretable. Maybe when you're building this up, you think about what, if you're looking for a specific object, what are defining characteristics of that object, and start trying to build features from contours based upon those characteristics. Sometimes, though, building your own features is tough. That's where feature detectors come. Feature detectors create an automatic representation of your image that can be used to extract useful information. So instead of you creating your own features, this does it for you. Useful is not in the reference to visualization, but object detection. It's not necessarily going to be a feature vector that you can understand what it means, but it's something that you can produce and combine with a classification method. One such method is the histogram of oriented gradients. So what that does is it creates a histogram of gradients binned by their orientations. We can do this because gradients include magnitude and orientation. And we care about this because large changes or edges should explain more of the image than the flat constant areas. So a little bit about how this works. Usually what you're going to want to do is you're going to pre-process or crop your image to fit this general size of your object. In this case, it's a 64 by 128. Then you define a square cell that you want to use. So in this case, you take your image and you divide it into 8 by 8 cells. In each one of these cells, you calculate the gradients. So in each cell, you can see here in an example 8 by 8, we have the gradient direction in the 8 by 8 cell, and on the right, the gradient magnitude. So you define your granularity of your direction. So here you see from 0 to 180, we have bins of size 20. In each cell, you place the gradient within the orientation bin. So for the blue one here, we see we have a magnitude of 2 and a direction of 80. So that goes directly into the 80 bin. But for the red one here, we have a magnitude of 4 and a orientation of 10, which is perfectly between the first two bins. So it splits it into 2 in the first bin and 2 in the second bin. So what this is doing is it's building up a feature vector to describe your image. But then you have to define normalization. The reason being is that you could have different lighting throughout your image. So it could read the gradients in different areas with more importance. So to account for lighting conditions, you take the image and you group 2 by 2 cells. So you create a 2 by 2 square of your 8 by 8 cells. You combine them and you normalize it. So what this ends up doing is it creates 105 histograms of length 36. Finally, you can cat them all together, and this gives you a feature vector of size 3,780 dimensions that should describe everything that's in your image automatically. So here we have the output of the histogram of oriented gradients. As you can see, it's not something that is necessarily human interpretable, but you do see a little bit of information from it just by eye. You can see that the dominant direction of the histograms explains the shape in the image. Along the line, you kind of see the histograms, the gradients being more vertical. You can see the same thing with the legs and the torso, the gradients lining up with the direction. So to implement this, unlike previously where you had to define your own features, you just take your image, you define what granularity of the orientations you want, how many bins, what you want to use for your number of pixels per cell, in this case an 8 by 8, and how many cells do you want to use for normalization. So in this case, 2 by 2. So finally, I'm going to do a little bit about neural networks because that is one of the newer things in image analysis. So you still can use some of the techniques from the previous sections of image analysis. You can sharpen your image and remove background, and then pass that data to a neural network. Additionally, OpenCV does have some neural network packages. So you can do this all in OpenCV if you want to. So a neural network just finds complex relationships between variables. I like to think of this as a very complicated way of doing something very simple. It just takes linear combinations of the inputs and determines if a threshold has been reached. So in this example here, let's say we're looking for a cat. This might be saying, is there a whiskers in this combination of pixels? Is there whiskers? And then the next one down, okay, is there whiskers in the top right of the image? Is there cat ears in the bottom left, etc.? One thing with a dense neural network is that the number of parameters are going to grow with the complexity of the data. So this is where convolutional neural networks came along. These are kind of the neural networks that are most associated with computer vision. It builds on the fact that the filters are translation independent in order to reduce parameters. The idea behind it was, if I'm going to look for a cat in the top left of the image is going to be the same as the cat in the bottom right of the image. I shouldn't have to have a separate set of parameters. So these filters, instead of taking a separate neuron for each combination of inputs, what it does is it defines a filter. Let's say it's looking for an eye, and it takes that filter and it moves it along the image, sliding across the image, saying, is there a filter? Is there an eye in this section? Move it into the next section. Is there an eye in this section, etc. Because you've removed some of the spatial dependence, that reduces the complexity. Additionally, you have pooling layers. Pooling layers help to reduce the size of your input. So you can see as you go along deeper into your neural network, the image width and height decrease. It goes from a 28 by 28 to a 14 by 14 to a 7 by 7. What this does is that it allows every set of pixels in your further in your image to see a wider range of your original image to build up more complicated features. Once you go further into the image, you then flatten it and you pass it to a normal dense set of neural network. So just a quick aside on what convolutions are doing. So feature maps that move across the image. One thing to note is that when I say this filter is looking for an eye and a face, that is something that's determined by the model. The model chooses the filters as it's learning through backpropagation. They help to remove the spatial dependence of features, and they shrink the image. So in this case, we have a 6x6 image with 3 filters, let's say RGB. And we have 2 separate filters, filter 1 and filter 2. In this case, it looks like filter 1 is looking for vertical lines. And so what convolution is actually doing is it's taking this 3 by 3 filter and applying it to the top left corner of the image. Once it does that, that combination of the 2 values becomes the top left of the 4 by 4 resulting square. Then it moves with a stride of 1 to the left or to the right or down and repeats the image. Now you can see the shape shrinks a little bit from a 6 by 6 to a 4 by 4. The reason being that you can only have move that 3 by 3 filter 4 times to fit on the image. If you go any further than that, then the filter would be sticking off the image. Additionally, because you only applied 2 filters, you're left with a 4 by 4 by 2 from your original 6 by 6 by 3. Pooling layers also help remove the spatial dependence. What that does is you can define, let's say, a 2 by 2 pooling layer, and you usually pick either average or max value. In which case, if you choose the max, it will take the maximum value in that 2 by 2 and use that as the input to the next section. So it reduces that 2 by 2 to a single value. As you go further down in a neural network, you build up more complicated features. The way they usually describe it as the early sections of convolutional network are looking for simple things, maybe lines, maybe certain combinations of colors, and the deeper layers look for more complicated features. So if for a cat, maybe whiskers, eyes, nose, etc. So another thing to consider with your CNN analysis is what type of analysis are you doing? Are we looking at an image classification, which would be, is this an image of a cat? If so, you can apply a normal CNN. Are you looking for where is the image in the cat? Where's the cat in the image? In which case this is object detection, and you might need to different architecture. Some examples are YOLO or TensorFlow object detection. YOLO is actually available in OpenCV, so you can use it straight from there. You could also try to extract out the exact area of the cat. So instead of a bounding box, drawing only the area around the cat. That's object segmentation. And some examples of that are UNets, fully convolutional networks, and masked FRCNNs. So finally, while all this seems like a lot, usually you don't do all of this by yourself. It's common practice to start with a pre-trained model when you're using a convolutional network, and then fine-tune it to your analysis. This is known as transfer learning. The idea is you take a model that's been trained on a ton of images, usually one example is ImageNet, and then you add your layers at the end of that neural network to focus on your analysis. Another reason for this is that these models have architectures that allow for deeper networks. The deeper network is, the harder it is for information to be passed back and forth during backpropagation. So usually these networks are created with that in mind. Some examples of neural networks that you can use for transfer learning are the BGG19, ResNet, Inception, Exception, and the big transfer model from Google. All of these have their pros and cons. So now into OpenCV with geospatial data. Angelique, you're muted.
Sorry, thank you. So going back, if you attended last week's workshop, we sort of talked about kind of an introduction to the type of geospatial data, and Sandeep went over raster data. So this is just a quick review of raster data and how it kind of fits into the types of geospatial data that's available. So with raster data, it's basically laid out in a grid. That could be sort of defined little squares in the grid, or it could be something as simple as a pixel in an image. These things can be generated from all sorts of images, and they can be categorical or continuous. And the example you see there, for instance, you could categorize this with the blue areas being water, the green areas being vegetation, and so forth. It could also be continuous in that measures could be sort of levels of a color, elevation, or other sorts of infrared levels, something like that, that is part of the data you have available. A raster stack is several layers of different types of raster data. And just to note that these are really big data sets, because you can have everything from, you know, categorized, understood data like watersheds, you can have elevation, you can have all sorts of different things kind of layered on top of each other and aligned based on the coordinates of that section of space. Next. So where does this data typically come from? Usually from kind of remote sensing data. Not always, but most of the time. And there you're taking information and images from satellites. So that could be, in some cases, just simple grayscale images. We could have color photos. But the nice thing about satellites is that they have the capacity to kind of go beyond the visible light spectrum that we're thinking about. So you can have also near infrared, you can have thermal images. There are also special satellites that do LiDAR, where you send basically up laser beams that are sending pulses of light and then kind of measuring how long it takes to receive that bounce back of signal so that you can very accurately measure elevation. Next. So, you know, in the last decade or so, really machine learning has really become kind of part of the set of tools that people who are doing geospatial analysis use. And for that, I think there are more traditional methods that have been used, but really machine learning's come in kind of in a big way lately. There are two main tasks that machine learning is used for: prediction and pattern detection. And I will note that Ben was talking about using machine learning, and that neural networks are a type of machine learning algorithm. And it's pretty easy to see how being able to do prediction and pattern detection can transfer over into the realm of spatial data. In the old days, you would use sort of different interpolation methods to sort of kind of fill in missing data. Like in this image you see here, we have temperature stations in South Africa, and the heat map is kind of combining raster data for elevation with the measures for temperature that are taken at each of those points. So we don't have temperature measures for anything that isn't one of those points. So using interpolation to sort of fill in the missing values. Pollution measures are similar. You can also use machine learning for pattern detection, such as detecting features across space. It's been used in research to measure deforestation or to detect areas of deforestation, or in Florida, red tide, which has some health implications, as well as making water usable at the time. Next. So going back to machine learning, OpenCV combined with machine learning models kind of enable you to do quite a bit of work at making image information useful. So just focusing for a minute on OpenCV itself, this is an example of using object segmentation with geospatial satellite images. So here we have an image of different kinds of circular agriculture in Saudi Arabia, because basically what they do is kind of allow water in a circular motion to enable agriculture in that space. And it's a pretty recognizable, roughly bounded area that can be seen pretty clearly from imagery. So there, in this example, they used OpenCV to segment those objects so that you could see and measure what is the agriculture, or what areas have been used agriculturally in that image and in that space. Next. Also, edge and boundary detection has uses with geospatial and satellite images. On the left, we see the use of canny edge detection to create a web map, which is fun and interesting, and I really like the picture, but I think a more useful use case is on the right, where they basically segmented this area of coastal space so they could differentiate between what was the coast and what was the water, and then used canny edge detection to look at what was the coast in 2014 and 2019, so that you could lay both of those on an image of the 2019 data and see how the coastline has changed. And that has, of course, implications for things like coastal management, land management, and so forth. Next. In addition, you can use it for other sorts of object detection. Like this is an example of sort of determining in a picture what is water and what is not. And here they used sort of more of the layers available within satellite imagery, because essentially they had to adjust it for vegetation. And there are two bands of satellite imagery that allow you to detect vegetation from other sort of features. So they used that plus thresholding to differentiate between dark objects like parks and dark objects like water.
Hey, Angelique, if you want to conclude, and I want to have like 5 minutes for question and answers.
I've only got a couple more slides in deep, so just keep it rolling. Go. Next. Here, again, a little more complicated. So this is object classification, looking at tidal space, combining OpenCV to process data, plus a predictive classification model to determine which areas were tidal flats, pools, and then sort of other features of a tidal flat. Next. Again, going back to the fact that satellites really give us a wider range of what can be considered an image, and that different sorts of light and different wavelengths give us different information. You can get, we can see more with infrared on some things than we would with visible light. And so each of these channels enable us to really kind of explore the space in a geospatial image and extract information from it. Next. And so last but not my last slide, see, Sandy, told you, don't have that much. The way that you can kind of utilize this multi kind of layered satellite imagery geospatial information is to add on the GDAL library into OpenCV. It enables you to import raster data. So here is the code for loading image. Here's the code for loading elevation data. And remember, when you're working with geospatial data, that you have to align. So if you have different layers, remember that all the coordinates have to line up so that something like in this image coastline is the same in one layer as it is in other layers of information. And so some pieces of advice in using that is avoid as much as possible using latitude or longitude data. Make sure you know the projection system for all of the data, and we talked on projection systems last time. Make sure that you align the coordinates, and an easy way to do that is to align at the corners. You can assign color values to elevation levels. And an example of this particular use case that generated that image, which is kind of a heat map of the elevation in this space using OpenCV to process it. The example of that code can be found at that link. So that's all I've got. So I think
Perfect.
5 minutes for questions.
Thanks a lot, Angelique and Ben. Wonderful presentation. And I will go ahead and read. We have 3 questions that are pointed towards OpenCV for now, but please type your questions for raster image analysis as well, meanwhile. So Ben, for you, the first question is from Robert Gunther. So is one use case for OpenCV is to facilitate the transformation of an image into a form which will be more consumable by Kira's CNN?
Yep, definitely. You can use it and you can transform it into something. Let's say an image has a lot of backgrounds, different types of backgrounds, and you don't want it to always care about just that background. Example being, I think they did an example with trying to figure out if something is a cow. Mm-hmm. And all the pictures of cows were always on grass. So when they had a picture of a cow in a city, they couldn't figure out it was a cow. So one thing you could do is you could try to remove out the background from the object you care about and use that as your input.
Okay, perfect. The second question is by our own Dave Castanaro. If convolutional layers learn their own features based on training data, and OpenCV has out-of-the-box filters to create features we know are generally useful, is anyone combining them as inputs into the same model?
So what you could do is, I think there are filters in different aspects. One of the things you could do is you can use inputs from OpenCV's filters, outputs from OpenCV filters as an input to your CNN. I don't think you can necessarily easily set, or it wouldn't be the easiest thing to set a filter from CNN OpenCV output, but you can combine at different parts of your neural network outputs of OpenCV as inputs to sections of your model.
Okay, I hope that answered your question, Dave. The third one is from Pradeep Das. During transfer learning, do you carry over biases built in the early data frames, or you can filter them out?
So if there is a bias in the early data frame, you can carry that over. One thing with a lot of these is they're trained on millions of images. So it's probably less biased than if you just had a small data set. They're going to see a lot more different types of each image. One thing you can do is you can choose if you want to freeze those previous layers in the transfer learning, or if you want them to continue learning. If you unfreeze it, it's a chance of removing bias with just your data, but that will take longer to learn.
Okay. And last question, I know we are over time, but last question that I want to see is, could you talk a little bit about issues of bias, gender, racial, political, etc., when dealing with image classification and identification? And could you talk about some possible ways we could try to identify and minimize these biases? I know it's a big question, but Angelique, if you want to talk about on that a bit.
I think basically if you want to minimize biases in how a model performs, you have more variety and diversity in the training set. I mean, honestly, it's a big question, but it's a simple answer.
Perfect. I hope that answers your question, Matt. And please reach out to either Ben or Angelique or myself, and we can talk in details about this question. And I'm super interested in this question as well.
And we will have at least one session, probably more, on that exact issue at our conference.
Yeah. Perfect. That concludes our questions.
All right. Well, thank you all so much, Benjamin, Sandeep, Angelique. Thank you so much for lending us your expertise today and your knowledge. Such a fascinating topic. And I do think we'll be able to share these slides. Is that correct, Sandeep?
Yeah.
Okay, cool. So we will, those of you who attended, we will send out a link to the slides. We'll also post them on Prepare's website. And we just want to thank all of you for joining us again. Have a great day, everyone.
Perfect. Thank you.
Bye, everybody.
Bye-bye.